There is a concept called random variable. A random variable is a variable that represents the outcome of a random process in an experiment, or in simple words, whatever we call it as variable in the outside world. This is a variable. Let us suppose you toss 10 coins. How many heads that you will get? You may get 2 heads, you may get 3 heads, you may get 5 heads. That is random. You cannot really say that you will definitely get only 5 heads. Sometimes you may get 6 heads, sometimes you may get 9 heads. So the number of heads in 10 coin flips is a random variable. The number of customers arriving at a store in 1 hour. I have opened a mall. In that mall, there may be 2,000 customers who can arrive. There can be one customer who's arriving. There can be 200 customers who are arriving. That is a random variable. The number of defective items in a batch. If I take a basket of apples, one apple can be rotten, or 2 apples can be defective, or 10 apples can be defective. That is a random variable. Lifetime of a light bulb is a random variable. Height of a person is a random variable. Waiting time at a bus stop is a random variable. Score, like daily rainfall amount, can be a random variable. Like anything that you see in the outside world which you feel that, yeah, this has some chance, it may change, it is a random variable. Temperature tomorrow, is it constant or a random variable? Temperature tomorrow, is it going to
Random.
be random, isn't it?
Random variable.
Yeah, random variable, like anything that varies randomly in the outside world, all of them are random variables only. What are not random variables? Number of planets. Is it a random variable? Today, number of planets are this. Tomorrow, will it change? Number of planets. Is it a random variable? In the
No.
planetary system, we
New
have fixed
planets
number.
can be
No.
discovered.
ठीक है, in a given, like in a given time span. Okay, number of planets in 2019. That was not a random variable, isn't it? Distance
Right.
between Bangalore and Delhi. Not a random variable. Constant. Number of days in a week. Is it a random variable? Does it change?
Constant.
No.
Year of birth of a person. Constant.
Constant.
Number of hours in a day. Number of pages in a book. The temperature of boiling water at sea level. Like once it reaches 100 degrees centigrade, then it will boil. So that is a constant. Anything that is a constant is not a random variable. The reason why I gave this these examples is like every now and then in every book, in every discussion, people tend to give the examples of random variable. But what is not a random variable? Sometimes we get curious. What is not random variable? All these constants are not random variables. Now, why do we even need to talk about these random variables? Because they are connected to something called probability distributions. In fact, the whole world, like we analyze the data, in that data set, every column is called as a variable. We have a column which says income, which is a random variable. We have another column called number of loans. So if I want to decide in a credit risk model, I want to decide whether this customer is going to be a defaulter or non-defaulter. Defaulter means bad customer. Non-defaulter means good customer. I will use variables like customer income. I will use variable like customer number of loans. I will use variables like customer late payments, monthly utilization. All these are variables or random variables, which we will use to predict whether a customer will get defaulted or non-defaulted. That will get converted into credit score. If I predict that there is a high chance that the customer is going to be defaulted, I will not give him the loan. Why should I give him? So probability distribution describes how a random variables are distributed. Even though they are random variables, there is a probability that we can associate with them. You know what? This is a random variable. It will change. But I can tell you with what probability a particular event will occur. That means if you roll a dice, number of outcomes, like you may get 1, you may get 2, you may get 3, you may get 4, you may get 5, you may get 6. But I can associate a probability with that. What is the probability that you may get 1? What is the probability that you may get 1?
1/6.
1 by 6. What is the probability that you may get 2? 1 by 6. You
Yeah.
may get 3, 1 by 6. You may get 4, 1 by 6. Now this is probability distribution. Probability distribution of a random variable will have two values in it. One is what is the value of the random variable, what is the probability of occurrence. This is the outcome, which is denoted by x. This is the probability of that outcome, probability of x. When you toss a coin, what is the probability of 0 heads? You're not, like if you toss a coin once, what is the probability of 0 heads? 0.5. That is a random variable. Number of heads that you get. Number of heads is a random variable. I may get 0 heads, I may get 1 head. Now tell me, if I toss 2 coins, carefully think and let me know what is the probability of 0 heads, 1 head, 2 heads. I may get 0 heads, I may get 1 head, I may get 2 heads. 0 heads, what is the probability of getting 0 heads when I toss 2 coins? When I'm tossing two
That's
coins, what are the probabilities when I'm tossing 2 coins? both the
Venkat,
part.
can we just write the outcomes the side that would be easier to calculate the probability?
Okay.
Actually,
Head,
combination of
tail,
both.
like that.
Yes,
Combination
I
of both,
think
right? 0, 0.
that is where we are comfortable,
Zero
isn't it?
zero.
Head, head,
Zero zero.
Yeah,
head,
yeah.
tail,
1/4, I think.
tail,
Tail,
head,
Tail
tail,
tail.
tail,
tail.
Head.
tail.
Tail
Zero
tail.
heads. What is the
Two tails.
probability?
1/4.
Zero heads happened here, which is 1/4. One head happened where?
1/2.
By 4.
One
One
head
by
By
two.
happened
four.
twice, isn't it?
Two by
Which
four.
is 2 by
One by
4.
two.
Two head happens
One by four.
1/4. This is the probability distribution of number of heads. So I would like to call this as the probability distribution of number of heads. When you toss two coins, you may get zero heads, one head, two heads, but the probability of getting zero heads is different. One head is different, two heads is different. There is a high chance that when you toss two coins, there's a very high chance that you may get one head, like 50% of the times. If you repeat this experiment n number of times, infinite many number of times, most often 50% of the times you will get one head. One out of the two coins will show one head, given that they are fair coins. Let us try to little bit take it into next level. Three coins. When I'm tossing three coins, zero heads possible, one head possible, two head possible. I'm talking about only heads. Three heads possible. All three can be heads also. Now, shall we write it? All three are heads, head, head, head. And then head, head, tail. And then I will say head, tail, head. And then there are
Tail.
eight possibilities, isn't it?
Head,
Head,
HHT.
H T is over. H,
Okay.
T, T.
HTT. Okay,
Yeah.
yeah.
I think an easier way, I'll tell you an easier way to write this. What you can do is you can take the previous one. Now these are the two coins. I'll
Mhm.
rewrite the same thing. You write HH, HT, TH, TT. Now you put the third one is all heads here. Now what are the other four options? The third one is
Tail.
all tails
Tail.
here, isn't it? The rest of the possibilities will be same. Now these are all eight.
Mm.
Now within these eight, there can be a chance of zero heads, one head, two head, three heads. If you try to count all of them, the probability of one head, the number of zero heads it will be happening only once. The probability is 1/8. Once only out of eight times it will happen. So once out of eight times, zero heads have happened, all tails, like somewhere here, all tails, one out of eight times. And then the probability of one head, it will happen thrice. One head has happened how many times? This is one head. This is also one head. This is also one head. So it happened thrice. The probability, now that probability is 3/8. Two heads is also 3/8. Three heads is also like everything head. It happened only once, which is 1/8. Now, why am I writing all this? If you're tossing four coins, now things get pretty difficult to track from there on. But what people have done is you can actually find a formula to find this is the outcome, to find the probability of this outcome. In fact, these are the coins. This is the outcome, number of heads. For this random variable, it follows a certain probability distribution, and you can actually generalize that probability distribution. That probability distribution is known as binomial distribution. Because if you keep on tossing like this, for already for three coins, we already exhausted. Now, four coins, five coins, 10 coins, if I'm doing an experiment with 100 coins, the outcomes are too many. That is too much. You cannot write like that. But there's a formula, like all these are actually following a certain formula. These actually you can derive using a formula that is known as binomial distribution. The binomial distribution is a probability distribution that models number of successes. For us, what I have defined as success, where is my bet on which side? What is my success in my experiment? We are always talking about what? Number of heads. So the
Heads.
number of successes in a fixed number of independent binary yes or no success failure trails. We have done three trails, four trails, or two trails like that. Where each trail has the same probability of success. The binomial probability formula is you don't need to calculate like the way previously we have done. Probability of exactly getting k successes in n trails. That means when you are tossing the coin four times, the probability of getting exactly two heads is NC2. Probability of success is 0.5 to the power whatever is the k 2, and 1 minus p 1 minus 0.5 is also 0.5 to the power n minus k, which is like 4 minus 2 2. This is the formula that you can use to actually calculate no matter what is n. Binomial distribution will tell us, for example, if I'm comparing this with the coin tossing, earlier we have counted manually. And then we have added, okay, zero heads, 1/8. Okay, three heads, 1/8. Okay, two heads, 3/8. One head, 3 by 8, like that we have counted. But if you want to replicate the same, you can use binomial probability distribution. Probability of getting 0 heads is nck p to the power k 1 minus p to the power n minus k. That is the formula. N is number of trails. We have 3 times we have tossed the coin, or 3 coins have been tossed. What is the probability that you will get 0 heads? 3c0, 0.5 to the power of 0, 0.5 to the power of 3. If you do all this math, you will get 0.125, which is matching here. If you want to
So
get
3C0, how does it come 1?
the formula itself, 3c0 formula is like, what is the nck formula? N choose k formula is what? N factorial divided by, what is the formula that is given? N factorial divided by n minus k
N minus k
factorial
factorial
into k factorial. If you try to do that, you will get this. 3 choose the 0. So that is what, like, it becomes 1. 3c3 also like that only. 3c3 also will be 1 only. If we like kind of substitute everything in that formula, like 3 factorial divided by 3 factorial into what, n minus k, 3 minus 0, like 0 factorial, which will be like 1. 3 factorial divided by 3 factorial, which will be 1. It's like that. Make sense?
Yes, it's a bit tough, but I hope there are some easy ways in Excel.
Yeah. If you want to know whether, if you want to get, like, say, 1 head out of 3 coin tossing, the formula earlier we have counted them manually, then we got 3 by 8. Now, if you put that in the formula, 3c1 into p power, like probability of success power 1, and n minus k, which is 3 minus 1, you will get 0.375, which is matching with this. So basically, a binomial distribution will precisely try to tell you in a given experiments, a fixed number of experiments, how many successes you may get once you give me the probability of success. Probability of failure, anyway, I can calculate by 1 minus of probability of success. We can directly tell how many times you may get that success. The probability of getting 1 success, 2 success, 3 success, we can get with that. So basically, n choose k. Like, what exactly n choose k mean? That means in how many ways you can choose. Let us suppose I have given you 3 apples. Those 3 apples are in a basket. Okay. And let us suppose, or there are 3 balls. This is red ball, green ball, and a blue ball. In how many ways you can choose 0 balls? You are not at all picking any of the ball. In how many ways you can do that? There's only a single
One
way,
way.
isn't it?
One.
We do not
One.
pick any. If I ask you to pick 1 ball, in how many ways you can pick that?
1 by
And
3.
choose 1. How many ways you can pick that? You can pick either red ball, leave these 2. That is one way. That is one experiment. Can you just pick a green ball and leave the rest of the 2? That is another way. You can also pick blue ball, give the rest of the 2. That is another way. That is what this 3c1 is becoming 3. 3c0 is becoming 1. Now let us see 3c2. I asked you to pick 2 balls out of them. Are you getting a hang of this? I'm trying to explain what exactly this nc1, like how come 3c0 is converting as 1. That means n choose 0. That means you're not picking any balls. That is only one way. You leave all the balls here. Now what if I asked you to pick 2 balls? How many different ways you can run that experiment? How many different ways? You can pick
3.
3 ways. You can pick red, blue, red, green, leave the blue. That is one way. You can pick blue, green, leave the red. That is another way. You can pick red, green, and leave the blue. That is another way. 3 ways are there. Now the third or the last experiment is I want you to pick all the 3 balls. I want you to pick 3 out of 3 and choose 3. 3, choose 3. I want you to choose 3 out of 3. How many different ways you can do that? You pick all of them in one go. That is only one way. So that's what this one. If you pick nothing, that only one. Once you can do it. If you pick 1, you can actually show me 3 different ways of doing it. If you pick 2, you can show me 3 different ways of doing it. If I ask you to pick all 3, you can only show me once. Like I picked all 3 in one go. That's it. There's no other way. That is what this n choose 3 means. Make sense now?
Yeah.
Yeah.
Yes.
Now let us do this 3 coin experiment on the Excel file. So let us, like, here we have calculated the probabilities. I have just shown you the formulas, but if we want to do it in Excel, I'm not sure whether you may have to do it or you don't need to do it. That is not really required, but I'll show it to you once. Okay. If you're doing the binomial distribution, now number of coins are given to you. Probability P is also given to you. Then you want to know, maybe the question could be, what is the probability that if this is the n, if this is the p, what is the probability that you will get x as 0 or number of heads are 0? When you're flipping 3 coins, what is the probability getting 0 heads, 1 head, 2 head, 3 head? So if you want to do it using binomial probability formulas, so the way you should write it here is, you write binomial distribution. It is asking for number s. First, it is asking number underscore s. S means success. So what is number s here? How many successes we are counting? That is this one, 0 successes. Trails. What are trails here? How many trails are here
Three.
in this experiment? 3. Now, can I freeze that? Because trails are kind of fixed. I will use F4 to freeze that. Probability underscore S. What does that mean? Probability of success. I will use this. Can I freeze that as well? F4.
Yes.
Cumulative, yes or no? There is another probability distribution called cumulative distribution. That means it will keep on adding until that probability. We do not want cumulative. We want direct probability. You will say probability, cumulative probability false. That means cumulative, what it does is it will try to give you the summation of probability with every row, which we do not want. So this is probability of 0 heads. If I drag it down, it will automatically take probability of 1 head, probability of 2 heads, 3 heads. These are the same probabilities, 0.125, 0.375, 375. Here we have done manual calculation. Here in Excel, it's happening. The same thing, even if I try to do it with 4 trails, and the probability number of heads can be 0, 1, 2, 3, 4. In that case, 0, 1, 2, 3, 4. The same thing will be repeating. No matter how many are you doing, the number of trails. This binomial distribution, the beauty is n can be anything. Still, you can find the probability. Are you with me?
Yes.
Yeah.
Can you explain the parameters for that binomial distribution formula once again?
Let us go through that. Maybe let's do it with 3. That is slightly easier. So imagine we are tossing the coin 3 times. So n is 3. And P, probability of success, is 0.5. So basically what we are doing is, whatever we have done here, getting the number of heads 0 or 1 or 2 or 3 when you toss 3 coins, we have already calculated, but we want to get it in the formula. So it will be, you will write binomial distribution. And then first you have to give number of successes. So you want to know 0 success or 1 success or 2 success or 3 success. That is number of success. My number of successes are in this column. I will select that. Trails. Trails means the value of n. In this case, trails is 3, isn't it? So I will select this one and I'll freeze it because n value doesn't change. F4 is what I have pressed. The next one is probability of success. Probability of success is given here. That also I can freeze it. That doesn't change. The next one is cumulative. Do you want cumulative probability? That means probability should be added until that point, or do you want the regular probability? We did not have any interest in cumulative probability. You will say probability, cumulative probability false. That means probability must function. Once you do that, this is for 0 heads. I'll just drag that. It will automatically take 1 head, 2 head, or 3 head.
Thank you.
The
So
same
when to
thing.
apply this formula for probability? So how do we identify whether
So
probability dealing with is binomial?
the kind of questions that you may get are, let us say, some of the questions may come like this. You have tossed 4 coins. What is the probability that you will get 1, 2, 3, 4 heads? That is like kind of toy examples. Maybe some of the industry questions will be, suppose you are working in a factory which is producing light bulbs. Historically, 2% of the bulbs are defective. Historically, 2% of the bulbs are defective. You randomly selected 10 bulbs. So what are the number of trails that you have done? You randomly selected 10 bulbs. So n becomes 10 here. For inspection, you have done it. Now, when you take 10 bulbs for the inspection, it may happen that all the 10 bulbs can be defective, isn't it? Extremely highly unlikely, but possible. 9 bulbs can be defective sometimes, 8 bulbs can be defective, or maybe only 1 bulb is defective or 2 bulbs. Like all the 10 out of 10 can be defective or 0 defective also possible. Now, you randomly selected 10 bulbs for inspection and you want to find the probability of finding exactly 1 defective bulb. Finding exactly 1 defective. So here, S becomes 1. Historically, what is the probability of defective or probability of S, which is defective? Historically, 2%, which is like 0.0. Now, for this, I can apply the formula 10C1 or 10 choose 1 into 0.02 to the power 1 into 0.98 to the power 10 minus 1, which is 9. So this is the probability that you may get one defective bulb out of the 10 that you have picked. Is there a probability of getting two defective bulbs? If I want to know that, then what is the formula? 10 choose 2, 0.02 to the power 2, 0.98 to the power 8, which is the probability formula. Is there a probability of getting 10 out of 10 defective? Possibility is there, but very rare. 10C10, 0.02 to the power 10, 0.98 to the power 10 minus 10, which is 0.02 to the power 10 itself. Like this is 1, 10 choose 1, 10 choose 10 is 1 into 0.02 into 0.02 into 0.02. It goes on for 10 times. So the probability is 0. Since it is 2 decimals, almost 20 decimals, and then the number actually starts 1 or something, which is very, very rare. It may happen that you may get 10 out of 10 defects, but it is very, very rare. So that is where we can use binomial distribution, where you have exactly two possibilities, success or failure, and you have done certain number of trails. And what is the probability that within those trails you may get 1 success or 2 success, 3 success, 4 success, like that. If I increase the n, if I increase the number of trails, the same coin tossing example, if I take n equal to 10, the probability of getting 5 heads is most prominent. I can get 10 out of 10 heads, I may get 0 heads, but that probability will be less. If I repeat that experiment with 30 coins, probability of getting 15 heads will be maximum. 14 or 16 also I can get, but probability of getting 30 out of 30 heads is almost negligible. 0 heads is also negligible. If I repeat that process 70 times, 70 coins if I toss, most often I may get 34, 35, 36 heads, but 70 out of 70 heads, that is like extremely unlikely, but still possible, very, very less probability. Getting 0 heads in 70 times if you toss a coin, that is also very less. If you repeat the process 200 times, most often you will get 100 heads, but getting 0 heads, getting 200 heads are also very less. But the probability itself, single event probability keeps on reducing. Getting 5 heads here is 0.25. Getting 15 heads here is 0.14. Getting 35 heads is 0.09. Like here, the probability keeps on reducing if you're talking about one event because the number of trails have increased. So after a point of time, if the number of trails, if n is very large, if the number of trails get into almost infinity, then the distribution that you see here, binomial distribution, tends to another distribution called normal distribution. So what is a normal distribution? Normal distribution is also known as Gaussian distribution or bell curve. It's a continuous probability distribution useful for the variables that are continuous in nature. In fact, most of the variables in this nature follow this natural phenomena of following the normal distribution. And the normal distribution is also known as bell curve. It looks symmetrical in nature. Bell, it looks like a bell curve. And right at the middle, you have this number. And then half of the data is here, half of the data is here. This is known as normal distribution, symmetrical. Heights of adults people. There will be some people who are very, very, having really big height. Some people are very short, but most of the times you will have the average height around that. People are very short or very less. People are who are very long are also very less. IQ scores. People are having very high IQ are very less. Very low IQ are also very less. Most often we will be surrounding this. Blood pressures. High blood pressure, low blood pressure. Very less people will be there. Average blood pressure. Most of the people will be there. Most of the variables in this real world follow a bell curve or a normal distribution like this. Reaction times or speed on a car highway. Let us suppose if the speed limit on a highway is, let's say, set to be 100. And then if we say that if you go below that, you will be fined. If you go above that, you will be fined. Then it will be a normal distribution where exactly 100 speed will be maintained by everybody. Very few people will be maintaining very less speed. Very few people will be maintaining very high speed. So this is known as normal distribution, and there is a rule that it follows. This is the formula for finding the probability of normal distribution, a little complex, but there is a better rule for us to know the probability of normal distribution. It follows a rule called empirical rule. So this rule, maybe you have to remember. In normal distribution, what happens is if you take the mean, and if you try to take mean minus sigma, what is sigma? Standard deviation. Mean plus sigma. So you have a mean plus or minus sigma, 1 sigma. 68% of the data will be there in that range, mean plus or minus 1 sigma. If you take mean plus or minus 2 sigma, 95% of the population will be lying in that. If you take mean plus or minus 3 sigma, 99.7% of the population will be lying there. Some people say that we are following 6 sigma limits. We are following 6 sigma, like our process is 6 sigma approved or something. Have you heard of it? Like 6 sigma,
6 sigma compliant.
6 sigma compliant. Yeah. So what they meant to say is they are right. How many percent of the time they are right? 99.7% of the time. They may go wrong only 0.3% of the times. 0.3, not even 1%. Less than 1%, 1/3 of 1%. So they are 6 sigma compliant. Apparently, the dabba wala in Mumbai, they are actually 6 sigma compliant. They pick up the dabba from the home and they deliver it at the office. Is there a chance that they may deliver our dabba, which is like our lunchbox, to somebody else? What they're saying is they are 6 sigma compliant. That means 99.7% of the times they never deliver it wrongly. Only 0.3% of the times they may deliver wrongly. That is what is a normal distribution rule. This is also known as empirical rule. Once again, what does this 68, 95, 99.7 rule mean? Within one standard deviation, 68% of the data. Let's say if you take IQ scores, and when I say IQ scores are normally distributed, maybe the mean of IQ score is 100, the standard deviation is 15. Then if you take any population, 68% of the people will be having the IQ score range of 85 to 115. That is 1 sigma. 95% of the people will be in the range of 70 to 130. That means if somebody has an IQ which is more than 130, he can boast about it. Why? Because this guy is better than what? 95% of the population. And 55 to 145 is 3 sigma, which is like what am I doing here? I'm taking 100 plus or minus 1 sigma is this one, 85 to 115, plus or minus 2 sigma is 70 to 130, plus or minus 3 sigma is 55 to 145. Anybody having IQ more than 145 or in this range of 145, they are the guys, they will be in the news and so on, isn't it? 145, roughly around 140-ish IQ scores. Is that true or is that a wrong example? Anyway, have you got the point that I'm trying to tell you here, all of you? 99.7% of the data lies within mean plus or minus 3 sigma. Now, there is one of the sample question that was given in the exam. Let us try to solve it with this knowledge. So look at this question. The distribution of day charges for customers in telecom company are described below. Assume that the charges are normally distributed. So assume that this is a normal distribution. What is the approximate interval where the middle 95% of the values are distributed? Middle 95% of the values are distributed where? Middle 95% of the distributed in mean plus or minus
2 sigma.
2 sigma.
2 sigma. So if you have mean, where is mean? If you have sigma, can you tell where the middle 95% values are distributed? Tell me what is the formula? Mean, middle 95 means mean plus or minus 2 sigma. Tell me the mean value. 30.63 plus 2 into sigma is 9.29. That is upper limit. 30.63 minus 2 into 9.29 is a lower limit. So this is somewhere coming around 49.21. This is somewhere coming around 12.05. So somewhere from 12 to 49 is middle 95% of the data distributed. If you get such question where the table is given, assumed normally, maybe exactly same middle 95 you may not get. Maybe if you get middle 68, can you solve it? Middle 68, mean plus or minus 1 sigma. Like that.
So basically, the answer of this question is 4 into sigma, right?
The answer of this question is the range will be 12.05 to 49.21. That is the answer.
No, basically, this guy is like asking 4 sigma only, right? From mean 2 sigma right, 2 sigma left.
What is,
That is
right. What is the approximate interval?
95%. So, mhm.
So let us see how the question was given and what answer we have to pick. Which was the question here? Maybe answers I haven't pasted there. Let us see. Is this the one? Yeah. So this is the question. We got the answer 12.05 to 14. Like this is the one that we have to pick out of this. Middle 95% are kind of in this range. Okay, that way. So for example, in this question, they have asked us like, what is the approximate interval where middle 95% values lie? Since they told that it is normally distributed. The moment I say normally distributed, I know that 95% of the values lie in plus or minus 2 sigma. Mean plus or minus 2 sigma. We took the mean and we did plus 2 sigma minus 2 sigma. We got 12.05 to 49.21. That is where they lie. Now the next concept is standard normal distribution. Now for a distribution, for a normal distribution, you can have any mean, you can have any standard deviation. But if you have a particular normal distribution whose mean is 1, whose standard deviation is, whose mean is 0, standard deviation is 1. Let me give you one normal distribution whose mean is 0. Mean is 0. Standard deviation is 1. Now tell me 68, 95, 97 rule. So for that particular variable, 68% of the data will lie between what numbers? There is a variable whose mean is 0, standard deviation is 1, and it is kind of varying normally distributed. So 68% of the data stays between where to where?
Minus 1 to 1. Yeah?
Minus 1 to 1. 95% of the data stays between
Minus 2 to 2.
minus 2 to 2. Around 99.7% of the data stays between minus 3 to 3. That is known as standard normal distribution. You tend to hear this very frequently. This is also known as Z score, where you have the mean of this variable as 0. Standard deviation is 1. There are multiple applications of it. Right now, we will not go to them. But if somebody says standard normal distribution, you have to recollect that it has a mean of 0. It is a normal distribution. Standard normal means normal only. Mean of 0. Standard deviation of 1. A similar question here. You check this. The distribution of day charges for the customers of the telecom company are described below. Assume that the charges are normally distributed. That means we are assuming normality here. Look at this. Assume that it is normally distributed. What approximately is the 97.5th percentile of charges? 97.5. What is this? 97.5 percentile. That means what is that charges value? Where below that charge, 97.5% of the data is there. Above it is 2.5 only there. This is little twisted related to previous one only. Middle 95. Middle 95 means how much is left? 5, isn't it? And it is symmetric. Here there will be 2.5%. Here there will be 2.5%. Can you tell me what will be the 97.5 percentile value if it is normally distributed? What will be exactly that value? What will be 97.5 percentile value if it is normally distributed?
So mean plus 2
3 SD.
into
Mean
3
plus
SD, correct.
3
3
SD or 2 SD? 3 SD
2
will
SD.
3 SD will consist how much data?
99.7.
99.7. Whereas here we are asking how much? 97.5th percentile. So what is 2 SD consisting? Mean plus 2 SD is consisting what? Plus or
95.
minus? It is 95. So when I say 95, it is middle 95, isn't it?
Yes.
If it is middle 95 means what I'm trying to prove here is if it is a middle 95, this remaining is 2.5, this remaining is
Plus.
2.5, isn't it? So that means until here, if I take this whole thing, can I call this as 97.5 percentile? Try to think about it. Is this really the 97.5 percentile? Because below this, 97.5% of the data lies or not?
Yes.
Isn't it? If this is middle 95, below this 97.5% of the data lies. So if somebody is asking us that approximately what is the 97.5th percentile, they have just turned the previous question into a different question instead of asking middle 95. I don't care about the left hand side. I am caring about the right hand side only. What will be this value? That will be mean plus 2
2 into
SD,
SD.
which will be mean is 30.63 plus 2 into SD. Like we have already done that math. Mean plus 2 SD, which will be 49.21. 97.5th percentile of the charges will be 49.21. So that is the answer for that question. Because middle 95 is a 2 SD, 2 plus or minus 2 SD. But somebody is concerned about only one side. I think this question was somewhere here. So answer is 49.21. It looks like a percentile based question, but it is actually related to the actual normality condition, that 1 sigma, 2 sigma, 3 sigma related.
Perfect. I think.
Sir, one moment, sir. So
Yeah.
you're saying that we are supposed to take 2 sigma, and that is, you're saying at the right side it is still the 97.5 percentile, is it?
Right. Because if we
Okay.
say, if I come here, I'm saying 68% of the data lies here. Okay. Already this side, 50% of the data covers, yes or no? If I'm saying like half of it will be there here, isn't it? This side is 50% of the data or not? This is middle value, median value.
Mm.
If this is median and from here to here 68% data covered, that means if I take this side, it is already 50% of the data. Now what other data is left here? So 68% means from here to here, how much of the data is left? Try to do that math. Just compare that. So I can get an idea. This whole side, remaining side is 50%. Out of that, 68, half of it will be what? 34 and
Oh,
34, isn't it?
yeah,
So until here, it will be 50 plus 34, it will be 84% until here, 84 percentile.
right.
Until here, it will be like whatever is this width. And here it is 97.5. It's like that. So if I'm concerned about only the rest of the data. So the question here is, what approximately is the 97.5 percentile? So to do that, in the middle one is 95. That means this is 2.5, this is 2.5. 97.5 means I'm getting a hint that everything until here is 2.5. That is why I took mean plus 2st.
Thanks.
Now there is something slightly different from the mean. Mean in probability distribution is actually called with a different name called expected value. Because earlier we have actual data. We were taking a summation of all the values divided by a count of all the values. But when you're dealing with the probabilities, then it is known as expected value. Expected value is also known as average value or the mean value. Sometimes you may hear a different term called expected value. So the expected value formula or the mean changed formula of the mean is actual value of x into probability of x. What is the actual value of x that may happen? What is the probability of x that may happen? For example, when you are rolling a die, you may get 1 or 2 or 3 or 4 or 5 or 6. But what is the average value that you may get? You keep on doing it. Let's say you have rolled a dice once, you got 2 as the number. You have rolled another time, you got 6. Another time, you got 1. You got another time, you got 9. Not 9, you will get 1. Another time, you got 3. If you repeat this process n number of times, if you take their average, what will be that expected value that you will get? You can get an idea by multiplying the actual value with the probability of that, actual value with the probability of that. So the average, if you repeat this experiment multiple times, the average number that you will get is around 3.5. That is known as expected value or the average value. Another example is, suppose if a lottery ticket costs around $5 and the price for winning is $100, the probability of winning is 0.01. That means 1%. Probability of losing is 99%. Now, what is the expected return that you get if you keep on buying these lottery tickets? Every day you keep on buying it. Every day you keep on buy that, buy that. Sometimes you may win that lottery ticket of $100. Sometimes you may lose that $5. Or most of the times you will keep on losing the $5. Like once in 100 times, once in a while you will hit that jackpot of $100. Again, lose the $5, lose the $5, lose the $5. If you keep on doing it, let us suppose I have done that experiment 1,000 times, 2,000 times, 3,000 times. After doing all that, how much money I will have on an average? So what is the expected average return that I will get? You can write the possibilities. If you win, you will get 95 only because $5 anyway you're buying it. That's why I'm counting it as 95. If you lose, you will lose $5. The probability of winning is 1%. You will get $95 from there. Probability of losing is 99%. You will lose $5 from there. So the expected value is $4 loss. If you keep on repeating this experiment, on an average, you will lose $4. Company always wins, isn't it? In lottery ticket, you will not only in lottery, in gambling, you will always be having something negative. Company always wins because they have to make some money because they are running the system. Somehow they have to find a way to make some money. Why we are talking about expected value? Because sometimes the same mean value that we have discussed, instead of asking you to calculate mean, you may get a question saying that calculate the expected value. So how did we calculate mean earlier? Tell me. If something like this is given, we used to find mid value. We multiply that with frequency. Do you remember the formula? Midpoint into frequency. Midpoint into frequency divided by overall frequency. Now, if you say frequency divided by overall frequency, this is xi, this is fi. So I wrote summation xi fi divided by summation fi. Now this is kind of changed. Fi by summation Fi is known as probability of Xi. So you can rewrite that as summation Xi into probability of Xi. So the mean formula just rewritten in terms of probabilities, which will give us the same value. So you write midpoint 5 into probability of that, 15 into probability of that, 25 into probability of that. This is known as expected value, which is 28.5. This is known as the expected value, or another name for mean. Why are we talking about it? Because there is one question in the exam. The day charges are like this, and the count of day charges are given here. So this is Xi, this is Fi. You can directly, if somebody asks you, declare the random variable m, midpoint of the charges. To illustrate the slab 0 to 10, it is m equal to 5. What is the expected value of m? When you see expected value, you can also calculate the regular mean. You will get the right answer. Otherwise, you can also use midpoint calculation, probability calculation, midpoint into probability calculation. That also you can do. So the way that we do is you calculate the midpoints, and then you calculate the probability. 30 divided by 2097, 220 divided by 2097. These are all the probabilities. X into midpoint, which is X into probability of that. This is the expectation. This is one more way of calculation. But if you find the previous method easy, which is actually easy, 5 into 30 plus 15 into 220 plus 25 into 243 plus all these divided by overall 2094, you will get the same answer. Both of them will give you the same answer. This is known as expected value because we are talking about probabilities, probability distributions. So the formula is kind of modified like this. Similar type of table you may get, and you may be asked to calculate the standard deviation. Earlier, the formula of standard deviation was summation xi minus x bar whole square divided by n under the root. Now that xi minus x bar whole square remains the same. So that fi divided by n, that is now called as probability. So this is the original formula that is now modified like this. Using this formula, you have to calculate standard deviation, find the midpoint, find the probability, x minus midpoint whole square, and then probability of x into x minus midpoint whole square. You will get the variance and the standard deviation. It is just the formulas and putting them in there. It's not really any new concept here. The standard deviation per se, the meaning of standard deviation won't change, but the way that we are calculating is coming from a different point of view. That's it. Otherwise, the values are also not going to change. So this is one of the exam question where you will be asked to calculate the standard deviation, where values are given. You are supposed to calculate midpoints, and then the frequency. You have to take care of this frequency and calculate the probability. And using this formula, you have to calculate the standard deviation. You can also use the formulas that I have given in the actual file, Excel file that I have given. Whatever the question that somebody is asking you, you can use the same formulas. Let's say if you go to standard deviation one, by changing these values, by changing the midpoint also, you can achieve it. Otherwise, you can try to understand what is happening in each of these formulas, because this probability calculation is not really difficult. And then once you calculate the probability, this into midpoint, this is x into this, x minus mu whole square, and then the multiplication of this, all of this. Our kind of formulas are pretty simple, but we just need to know what is the formula that we need to keep. I would call this as looking at standard deviation, looking at mean from the probability distribution point of view. Now comes the actual last topic for this discussion. There's something called sampling distribution. What exactly is sampling? It is impossible to access population all the time. For example, in India, if I want to know average age, reaching out to every person in India and taking a note of age is going to be impossible. Sometimes accessing population is literally impossible. If I want to check the quality of milk in a factory, literally checking every drop of milk, it is not viable, practically impossible. We should not do that. You will take a sample. So the terminology goes like this. You have a population, and any measure that you calculate on population, they are known as parameters. Usually you call them as population parameters. If you have full population parameter mu is a mean. Population standard deviation is a population parameter. If you take a sample from there, and if you calculate the same mean, that is known as sample statistic. So you will hear this term called statistic versus parameter. So when you see that next time, P means what? When somebody says parameter, they are talking about what? They're talking about a metric that is calculated on population. When they're saying it is a statistic, SS, when somebody says this is a statistic, what does that mean? It means it's a metric that is calculated on a sample. Now, what is sampling distribution? A sampling distribution is the probability distribution of a sample statistic that is formed when a size of n is taken repeatedly. For example, you have a population of 10,000 individuals. What I'm doing is I'm taking 300 individuals from there. I have taken their average age, that is average age 1. I have taken another 300, that means again I kept them back. Out of 10,000, again I kept another 3,000 sample. I found their average age, that is x2. Again, from 10,000, I picked another sample. I found their average age. I repeat that experiment multiple times. Then I have age 1, age 2, age 3, age 4, and so on. So the distribution of average ages in the sample, that is known as sampling distribution. Now, if you read this, it will look slightly better. A sampling distribution is a probability distribution of a sample statistic. Can you tell me what is the sample statistic that I'm talking about in this case? What is the sample statistic that I'm calculating?
Sample of 300 folks.
Average age is the statistic and the sample size is 300 is the sample size. Here n is 300 formed when a sample of size n is repeatedly taken from population. So I'm taking a sample of 300 guys and every time I'm calculating their age. And the distribution of such age or the average age that you get from all these samples, that is known as sampling distribution. And why we need to talk about sampling distribution of a sample statistic? Because it is connected to central limit theorem. What central limit theorem, commonly known as CLT, what it states is, no matter what is your population, no matter what distribution it follows, if you take sample mean, if you take a sample and if you take the mean of that sample, any variable, that always follows normal distribution. That means earlier experiment, whatever I have done, I've taken sample 1, found the average age. I've taken sample 2, found the average age. Sample 3, found the average age. If I repeat it multiple times, then what happens is the average age follows a normal distribution. The average age follows a normal distribution that is given. No matter what is the population, maybe in the age is not following normal distribution inside the actual population. But what central limit theorem states is, if you repeat an experiment multiple times, no matter what is the original population, the sampling distribution of any statistic that you are drawing will be following normal distribution. That is what they mean to say. Once again, what central limit theorem says, it states that regardless of shape of the population distribution, regardless of whatever is the shape, the distribution of sample mean for sufficiently large number of independent identically distributed random variables will tend to be normal or bell shapes. In other words, the sample size becomes large. The sampling distribution of a sample mean approaches to normal distribution. Now, why are we discussing central limit theorem here? What is the reason? That is connected to something called confidence intervals. Now, that is the final result. Why we are talking about central limit theorem? Why we are talking about sampling distributions? What is the reason? What is the whole connecting point here? Where are we ending this? All of that is connected to confidence intervals. So let me repeat this once again. Then once I tell you about the confidence intervals, then we will see the relevance of all this. What is a sampling distribution? You take a whole population. From that population, you take sample 1, find the mean of that. You take sample 2, find the mean of that. You take sample 3, find the mean of that variable, any variable. You take sample 4, find the mean. You repeat it multiple times. And the distribution of all those means is known as sampling distribution. And central limit theorem says that that distribution, for example, from the population, you keep on taking the average age, that will follow a normal distribution. Now, why this normal distribution is important? Because that is connected to our confidence intervals. A confidence interval is a range of values derived from sample data. Look at this carefully. Confidence interval is a range of values derived from sample data that is likely to contain true population parameter such as population mean or population proportion. What it means to say is, we want to talk about population. Imagine in India, I want to find out what is the average age of an Indian. It is impossible for me to find out the average age because I cannot access everybody in this population. What you can do is you can take a sample, but nobody will accept your sample because people will say that How can you take a sample and make a conclusion about the population? Now to defend that, you know what? I took a sample, which is unbiased sample. I found the average age. Now I can give you 95% confidence limits according to central limit theorem. I found that the average that we are calculating on the sample, it is always normal. So by using that, I can tell what are the 95% limits in the population parameter. So we can talk about population parameter based on a sample statistic. That is the whole point of these confidence intervals. That means I can say that based on a sample of 100 students, the 95% confidence interval for population mean height is this much. The population is huge. There are 1 million students are there in schools, but I have taken a population of sample of 100 students and I found their average height. Now I can tell you the confidence interval. Maybe based on this, I can tell you 95% of the times the student's height lies here. Based on a sample of 50 cars, I can tell you the 95% confidence of mileage. It is always lying between 30.1 to 32.5. Using a sample of 50 batteries, the 99% confidence intervals are 8.7 hours to 9.3 hours. Based on survey of 150 residents, now 95% confidence interval is this is the income range that people are lying in. So you can make these kind of confidence intervals if you have a solid theory which says that the sample follows a particular distribution. So that theory is supported by central limit theorem. What it says is if you keep on taking, let us suppose if you have a population and if you do not know what are the numbers in that, if you keep on taking samples, the sampling distribution is always normal. So there is a formula that is given for central limit theorem and finding the confidence intervals. You take the sample mean and then you add z into whatever is a sigma divided by root n. So what it tries to give you is you will be able to tell the numbers like this, the way that we have given. You find the sample mean height, and then using this formula, you can always tell that the population mean will be somewhere in between this. You can take a sample of 50 cars. You can say population will lie in this if you have this confidence interval with you. So the main connection between this confidence interval and central limit theorem is this completely relies on the central limit theorem, because central limit theorem, we gave that the sampling distribution of a sample statistic is normal distribution. As an example, what we can, let us suppose if you have a factory which produces light bulbs, it is impossible to test every light bulb that is produced by the factory. But somehow we have to give to our customers that our light bulbs will actually stay good for these many hours, isn't it? But it doesn't mean that you keep on testing every light bulb. That is impossible. So if you want to tell about your mean lifespan of your light bulbs, I want to say 95% of the times my light bulb actually stays in this hour. If you want to do that, maybe take a sample of 100 light bulbs and you found the average is 800 hours. For 100 light bulbs, average is 800 hours. That means you have in this formula sample mean, which is 800 hours. And then n is you have taken 100 light bulbs. Then the standard deviation is 30 hours. You have the sigma also. Then you can tell what are the confidence levels or confidence interval for that particular lifespan of the bulb. So you will substitute all these values, 800 hours plus or minus the z value is 1.96 for 95% confidence. And if you put all these values, you can say that there is a 95% confidence that my light bulb will stay minimum to minimum 794 hours, max to max 805 hours. This is my confidence interval. Confidence interval calculation is done based on the sample to estimate anything that is related to population parameter. A question that is related to these confidence intervals is also given in that sample paper. So this whole theory which says that they have pulled in 81 moviegoers. That means here in our case, n is equal to 81. And the average pledge amount is the average value or the sample mean is 5,400. Can you tell me what are the approximate 95% confidence interval for the whole population? So once you have n and somewhere the standard deviation is also given. So the formula is sample mean plus or minus z into sigma by root n. So what is your sample mean? Sample mean is 5,400 plus or minus what is the value of z that you have, that is 1.96 into sigma is 180 divided by square root of n is square root of 81, which is like 9. And then from here you will get those numbers to get the lower limit and the upper limit.
Where's the 1.96 coming picture?
So the z value for 95% confidence limit. Okay. So 95% of the data, lies somewhere between minus 1.96 to plus
Oh, okay.
1.96. Like
Got it.
roughly we call it as 2 sigma, but it is actually 1.96 sigma. That is where
Got it.
95% of the data. Maybe you can take this formula and think that if I have a sample value, if I want to estimate what are the population parameter 95% confidence limits, this is the formula. I tried explaining the formula, but it has a central limit theorem and other sampling distribution internally in it. Maybe you directly take the formula, we will accept the theory and directly try to find the values. Okay.
So 1.96 to 95% confidence I could not relate to. How this number came?
So 95% of the times, our data lies between plus or minus 2 sigma, isn't it?
Yes, yes.
So the 95% confidence, like this is minus 2 sigma plus 2 sigma. But in reality, it is not actually 2, it is 1.96 sigma in reality. So that is where that 1.96 Z value, if I want to know 95% confidence limits, I should have kept Z value 2. But in
So if
reality,
you
it
use
is
2 also, will the answer be wrong or correct?
like 1.96 is widely accepted. Yeah. The histograms are similar to the range charts that we have seen here initially. So basically, if I try to draw this from 20 to 29, 10 people are there. From 30 to 39, 8 people are there. And from 40 to 49, 12 are there. Like that. So if I try to draw this, like minimum value is 0 and then 20, 20, 30. Now from 20 to 29, 10 are there. Maybe I'll take this as, let's say 5 and then 10, 15, 20. From 20 to 30, there are 10 people are there. So this will be the first bar. And then 30 to 39, 18 are there. So this will be the second bar. And then from 40 to 49, 12 are there. And then 50 to 59, 8 are there. Somewhere here. And then 60 to 60, then 2 are there. Maybe the questions that you may get may be related to percentiles that we have seen. What percent of the data is below 59? Or what percent of the data is above this? Or maybe in histograms, you may get questions on skewness. Is it left skewed? Is it right skewed? Or something called kurtosis. Skewness means the curve is skewed to one side. Okay, either left skewed or right skewed. Like you may get a diagram of histogram and ask, you may get a question saying, is this left skewed or right skewed, or what is the skewness value? And another question that you may get is on the kurtosis. That means, is a histogram chart looking like this, or is the histogram chart looking like this, or histogram chart looking like a very sharp one? Is it going like this? Like if it is looking like this, platykurtic, I think leptokurtic, mesokurtic, like that, there are different names or the kurtosis. You may get questions related to skewness and kurtosis if the discussion is about histograms. So if you look at this one, question number 1 is related to conditional probability. We solved it. Next question is also conditional probability. You should be able to do it. Next question is related to middle 95%. What is this related to? Middle 95%. If you're solving this type of question, what are you going to look at?
Mean
Mean
plus
and
minus.
standard deviation.
Yeah, mean plus or minus 2 standard deviation. 97.5 percentile, which is also mean plus or minus 2 standard deviation. Now this is, let us see the question. This one also we solved it, isn't it? How many
Yeah.
customers are actually churned? What is the percentage? And this one is expected value. For calculating expected value, how do we do it? Once the range is given, you
Mid
have
into
to,
probability.
mid value, mid into that probability. Perfect. Standard deviation also, extended formula is given for that. Now, this one, a spreadsheet contains monthly salaries of 100 faculty members, and everywhere if we increase, does the standard deviation change? Standard deviation remains unchanged. And you have quartile 1, quartile 2, quartile 3. Where does the upper end begin? That also we have. Tell me what is the upper end for outliers. Recollect it.
Q3 plus 1.5
Q3
IQR.
plus 1.5 into IQR. Who is
IQR.
that? You are going to get. Yep. Upper end is Q3 plus 1.5 into IQR, isn't it? We discussed that.
Yes.
And I think this is the last one related to this confidence interval. Confidence interval is something that has little dense in theory. So that's why I directly gave you the formula. Usually you will get this only 95% confidence interval. You directly input those values, identify what is N, what is the sample size, identify what is the average, identify what is the standard deviation. And if it is 95% confidence interval, directly you can substitute everything in that formula. You will get lower and upper limit. So that is the story for today.